You're listening to the FQxI podcast. Today.
And the idea of Panspermia was that life on Earth came from asteroids and comets, and that they seeded life on Earth. And this is kind of suggesting that maybe that might not entirely be true, but at least that the ingredients for life may have originated on asteroids. I feel like these guys just deserve it for the fact that they literally spent 20 years working on this project.
We're counting down the biggest physics stories of 2025.
First thing that came to my mind when I saw this report was, it's like that question from the electric boat company from 30 years ago. Why are manhole covers round? Maybe I'll quote Terry Tao, who's a very famous mathematician. He says, it's like perfecting a perpetual motion machine. They're getting more at the output than the input.
With quantum physicist Ian Durham.
Yeah, everybody wants, wouldn't it be cool if we had these? Well, yeah, sure, maybe. But, it's also interesting to know that they can't exist. That's a pretty profound and deep thing. Let's just put it this way. This was a big enough story that I changed the class I was teaching at that time to incorporate this.
I'm Zeeya Merali. Welcome to the End of Year podcast from the Foundational Questions Institute, where we are reviewing the biggest stories in physics and foundational science of 2025, as picked by Ian Durham, a quantum physicist at St Anselm College in New Hampshire. So, hello again, Ian Durham. It's that time of year. We're in December. We're looking back at 2025 and all that was good and all that was bad. How are you?
I am here, which is good.
I am here. Okay, well.
I am here.
That's the least you could say, I guess.
Yeah,
Yeah, people can't see you, but you are also wearing a Santa hat.
I am.
What's happened to your basement? Usually you're in your basement.
Oh, isn't that a fun story? We have a mouse infestation.
Oh.
So the basement is currently unusable. Hence you asked how things are going. Well, that's how things are going. Because normally I would be in the basement and it would be perfectly fine. But nope, the basement is currently unusable. But otherwise, I'm doing well.
Think of the mice as your little helpers in this endeavor of choosing the biggest stories of the year. Lots of, interesting and intriguing choices. Some really, really good ones. A few that, I've had a sneak peek at your list where I'm wondering about the ordering slightly, but we shall come to that. Should all be good fun, I think. But yes, before we get to the list, before we even get to the pre-list of runners-up, there are a few sort of announcements about FQxI that we should make, some news we should catch up on, and I think to start on a somber note, we should say that we are recording this in the middle of December.
Indeed.
I think probably less than 48 hours after the news of a shooting, I should say yet another shooting, at a school, at a place of learning in the United States. This time at Brown University, which is where I did my PhD. Eerily enough, I suppose, for me, at the Barrison Holly building, which is the engineering and physics building. Brown University is close to the hearts of many of us at FQxI. Our president, Anthony Aguirre, studied there. One of our board of directors, Pinar Emiradag, studied physics there. And a lot of our FQxI members have a close relationship with Brown, having studied there, having worked there. This is not to say, that this makes this tragedy any worse than the many, many, many others that have been happening. And goodness me, on the news, a few hours later, there were more tragedies around the world, more shootings, more horrific stories. But I just felt that, we should say something just to commemorate this. It's a physics department. It wasn't a physics class, but it's something we have a personal connection to. So I just wanted to say, condolences to everybody involved, to those that lost their lives, to their families, to their friends. It's just an awful thing that's happening. It seems to happen much more in the United States. Ian, you're a professor in the United States. I don't know how these kinds of incidents affect your daily life, if they do, or if you just put them to the back of your mind and just hope for the best or not think about it. How do you react to this onslaught of stories every year?
Well, so I'll just say this. So a former student of mine who graduated close to 20 years ago, um, her brother was one of the victims in the Virginia Tech shooting 15 to 16 years ago, something like that. I don't remember when it was. So I know it intimately well in that sense because I still stay in touch with her. I know her mother too. And so, yeah, I don't know. There are times when I like, geez, do I really want to go to work tomorrow? Yeah, I just wish we'd have less violence in the world. It is difficult to deal with it on such a daily basis and to be in an institute of higher education or a school, period, because so many of them happen in schools.
That's not a very bright note to start this year-end rundown with.
No.
But it felt wrong not to mention it since it happened so recently.
Yeah. And this is supposed to be a happy season.
I'm not sure that we can naturally segue away from that, but like I said, it just felt like something that had to be really acknowledged up front as we start off this look back at the year. Let's get to some FQxI announcements. We have just launched a masterclass with Julian Barber. Ian is nodding his head. Julian Barber is a very eminent physicist with lots of radical ideas about reformulating physics, sort of rewriting general relativity, rethinking time, whether or not time exists, whether we can sort of reframe physics without any sense of scale, but in terms of shapes and shape dynamics. And we've got a little mini masterclass of 3 brief lessons that you can now join and take part in and enjoy. I want to say thank you to everyone that has already signed up for the masterclass, earning their FQxI Q Academy certificate. We have had hundreds of happy students already. For a limited period until the 7th of January 2026, we're offering you a massive 70% discount on the sign-up fee. So if you go to the podcast page, qspace.fqxi.org/podcasts, and look for the link, or just go to QSpace and look for FQxI's Q Academy, and I'll also put a link on YouTube in the show notes, and you sign up right now, you can join Julian's masterclass for the bargain price of just $3.30 for the first month's subscription, so you're not paying the full $11. Or if you prefer to just give a one-time payment, then you can pay just $16.50 for 6 months of access, and that's down from the usual price of $55. So yeah, a really, really great bargain. You just have to type the coupon code podcast70 at the checkout or use one of the links provided, and that will automatically give you the 70% discount. Again, this offer won't last forever. You have until the 7th of January to use the coupon code podcast70 to get that 70% discount on Julian Barber's new masterclass. Please don't miss out, and please remember that FQxI is a non-profit organisation, so the money that you give will be put back towards making more masterclasses, making more podcast episodes, and even supporting the research of physicists like Julian Barber, like Ian Durham, and like so many of the others that FQxI has funded over the years. And Ian, this should be of interest to you because we have, as we've been promising, been developing a masterclass with you, a much longer, more detailed one.
Yeah.
We've recorded one episode of it.
We have, and we're going to be recording more in a couple of weeks.
With mice, I believe.
With mice, yes. No, hopefully the mice will be gone by that time. If not, I'll put them in neat little costumes and things, and they can be my little helpers.
Could use them to do little experiments and stuff. You could do a superposition of mice. Yeah.
Instead of a cat in a box, it's a mouse in a box.
Yeah. What else do we have? So in other exciting FQxI news, or at least to a podcast announcement regarding yourself and myself.
Well, really you. This is not me. This is all you.
Well, it's not the FQxI podcast that's part of this announcement, but you did help me by collaborating and being interviewed on another podcast episode that I made for Nature. So this little Nature podcast episode that we put together, it also involved George Ellis and Chanda Prescott Weinstein. It was part of the What's in a Name series. run by Nature, 3 episodes that covered all sorts of things about naming conventions in science, from viruses to hurricanes to different kinds of species. And we were on the physics episode, which sort of discussed various terms in physics and their origins and how there's some ambiguity in the choice of words, choice of terms. Things like the Big Bang, dark matter, dark energy. Ian came in as the quantum expert and talked about spin and the word quantum itself and a few other things. And yeah, we won a little award earlier this year for the whole series. A Lovey Award for Best Podcast Series, or in the category of Best Podcast Series. I hope I'm not misspeaking there. Which was nice. It wasn't even sort of science speciality. It was a general award. This is a big European award for podcasts. So, yay.
Yay. Congratulations, Zeeya. It was all Zeeya.
Well, it wasn't all just me. It was also Benjamin Thompson, the producer, Noah Baker, who also helped produce. And there are 2 other episodes out there that you can listen to, one hosted by Benjamin Thompson himself and another by Charlotte Stoddart, and I will put links to that on the podcast page qspace.fqxi.org/podcasts if you want to listen to it.
I recommend it, not just because I'm in one episode. It's a great series.
You might have like the opening quote as well, if I'm not mistaken, I think.
Could be.
Well, people will have to listen and correct me if I'm wrong. Right, here we go.
Top 5.
I think we're going to do the same thing as we did last year, Ian.
Okay.
Where we have a list of runners-up that did not quite make the top 5, but we are not going to put them on the main podcast. So if you are listening to this through your podcatcher or on YouTube, you're not going to hear the runners-up. You are going to have to go to qspace.fqxi.org/podcasts and click on the bonus material to find out about the runners-up. And frankly, I think some of these runners-up could have made the main list, and maybe that'll be something we chat about. I don't know.
Mm-hmm.
And after that, come back and listen to the actual top 5. One thing to say, we will be repeating the same thing that we've been doing for a couple of years now, which is that if you find yourself on the list of the top stories in physics of 2025, then get in touch. You could maybe be eligible for an FQxI hoodie, t-shirt, mug, whatever else is on the FQxI shop. Go to qspace.fqxi.org, visit the shop, find your own merchandise. If you are a winner, get in touch and let us know. Right.
All right.
Ian, here we go.
Here we go. All right. So coming in at number 5, they have found organic material on the asteroid Bennu, including, and this is my favorite, something called tryptophan, which if you are an American and you celebrate Thanksgiving, you will know all about tryptophan, because tryptophan is an amino acid that's in turkey, which we eat on Thanksgiving, and is at least legendarily responsible for the fact that every Thanksgiving afternoon people get sleepy and take naps. So apparently there's tryptophan on asteroid Bennu, along with other amino acids.
So this is from an analysis of 120 grams of asteroid dirt collected by NASA's OSIRIS-REx mission, which visited the near-Earth asteroid in 2020.
This also gives me an opportunity to talk about one of my favorite topics. But I studied alternative cosmologies when I was in grad school. And one of my favorite people that I encountered in all the study was Fred Hoyle. And Fred Hoyle had all sorts of crazy ideas, including one called Panspermia. And the idea of Panspermia was that life on Earth came from asteroids and comets, and that they seeded life on Earth. And this is kind of suggesting that maybe that might not entirely be true, but at least that the ingredients for life may have originated on asteroids, because these asteroids, Bennu, this one in particular, is just absolutely chock full of all sorts of organic molecules, which is pretty wild. Now, I do want to say, space is a wild place. So there are literally clouds of urea in outer space. And if you don't know what urea is, look it up. UREA. There are clouds of that in outer space. So there's a lot of weird stuff out there. But we don't know where life came from. Like, no one has ever been successful in creating life in a laboratory out of like non-life ingredients yet. But the strong suggestion that it had something to do with amino acids and proteins and things that were floating around, these organic molecules. And then maybe there was like this giant bolt of lightning and suddenly, poof, there was life or something like that. So the fact that we found them on an asteroid is pretty wild.
Tell us about some of the things that were found on this asteroid. So there were certain salt residues, for instance. Why is that interesting?
They did identify a whole range of salt minerals, including a bunch of carbonates and sodium-bearing phosphates that were apparently formed when, I guess there was originally liquid water on this asteroid, which is cool. Life tends to exist pretty close to the range of liquid water, which, by the way, is a very narrow range. Like, liquid water only exists between 0 and 100 degrees Celsius. And life tends to exist somewhere around there. So there was water, there was probably salt water on Bennu or on whatever it was part of once at the start of the solar system. It was basically like a brine, like if you make a pot roast or I don't know. I don't really cook, but maybe a brine, a pot roast or turkey or something like that, right? I don't know. I just know my wife talks about brining things. So this liquidy, briny thing would have then frozen out and you would have got these salt minerals. The brines kind of play an important role as being like
it's like a scaffolding.
Yeah, like a scaffolding. They help organic molecules build. I've seen it told that phosphate is a little bit like a pegboard that's got holes and the atoms use those spaces to arrange sugar molecules. And so that's how some of these more complex things form. They also found these ambidextrous amino acids. I didn't realize that amino acids had arms.
Dear. It's a Santa hat. It's just encouraging you to bad jokes, dear.
I know it's the Santa hat. So molecules in nature, many of them have natural chirality. So they can be either what we say left-handed or right-handed, which has to do with their rotational symmetry. So how they're symmetric in terms of how they rotate. The chiral aspect of molecules, what's fascinating is that life always seems to come from left-handed amino acids. Another way to think about it is you can never, so I got my left hand and my right hand, I can never twist my left hand around. No matter what I do, I can never match it up with my right hand. Try that, but don't break your wrist. And amino acids can either randomly be left-handed or right-handed. But the thing is life only ever comes from the left-handed ones. And we don't understand why that is. And one of the things that they were looking at was in these amino acids was for maybe some kind of preferred chirality. But as far as I know, they didn't find any. So we're still not sure where life comes from or why it comes from left-handed amino acids.
So that's still a mystery. And then there seems to be another mystery, although obviously the origin of life is one gigantic mystery.
It's a huge one.
So it might be a bit ambitious. That definitely would have got to number one if they had solved the origin of life, I feel.
Yes.
But I guess another mystery then is why on this asteroid there were sort of a certain level of complex organic molecules, but only up to a point, and it didn't kind of go further. So I guess there's a question of, is there something on Earth? Maybe life couldn't exist anywhere else, but the ingredients could get to Earth, and then something else happens here that could trigger life. Who knows? Yeah,
like no one has ever found RNA or DNA, which by themselves are not life. But no one's ever seen those molecules anywhere but Earth. There's nothing more complex than just the plain amino acids on Bennu. So you go from those amino acids to this complex string of nucleobases, which is RNA or DNA. And we only found that on Earth. And nobody knows why.
Do we know where Bennu came from?
I don't know where Bennu came from. Do they know where Bennu came from? I really, look.
Who knows?
Presumably it came from some larger body in the early stage of the solar system that formed and then got obliterated from all the other stuff bumping into it.
So the stories tell us that upcoming missions such as NASA's Dragonfly and JAXA's MMX will deepen research into extraterrestrial organics and shape future science and exploration policies. So, there we go.
But for now, if you want to get that sleepy feeling from Thanksgiving turkey, but you don't want to actually eat the turkey, just go to an asteroid.
Just go to an asteroid. Just lick an asteroid.
Lick an asteroid. There you go. You'll get your tryptophan that way.
Or listen to our podcast. And, that could probably put people to sleep without having to eat any turkey. Yeah, I don't know. No, it's far too exciting for that. Nobody would fall asleep while listening, especially to the top 5.
We hope so. Yes.
Yeah. As we come now to
number 4.
To number 4.
So, number 4, I feel like these guys just deserve it for the fact that they literally spent 20 years working on this project. They're actually chemists, so we're giving our award to chemists.
Oh, dear.
I know, oh dear. But they actually have observed superfluidity in a hydrogen molecule for the first time. Superfluidity had been observed in helium and in Bose-Einstein condensates, but it was never observed in just plain old molecular hydrogen until now.
So this was an international team led by Takamasa Momosa and colleagues at the University of British Columbia in Canada. Ian, tell us, what is superfluidity?
So all gases and liquids are, broadly speaking, fluids. Fluids have a measure called viscosity. The higher the viscosity, the thicker the thing is, right? So honey has a really high viscosity. It doesn't flow well. It's a little bit like friction, but not quite. It's a measure of flow. How well do the molecules move around each other? Do they interact with one another so that maybe they slow things down a little bit? It's a little bit like a fluid form of friction. A superfluid then, a superconductor is a conductor that doesn't have any resistance. Well, a superfluid is one that doesn't have any viscosity.
Why did it take 20 years for them to do this? What made it so tricky?
So superfluids are prediction from a variety of theories, thermodynamics and quantum mechanics and things. They usually occur at relatively cold temperatures. Indeed, this particular story, they were able to do this at 0.4 Kelvin, which was tricky to create the superfluid at that temperature because that's getting darn close to where hydrogen, actually I think it's below where hydrogen actually freezes solid. So they had to keep it a liquid. So what they did in this particular case is they somehow got little clusters of these hydrogen molecules inside helium nanodroplets. And then they embedded a methane molecule inside the cluster of hydrogen and were able to look at the spectroscopy from the methane to see that they were actually able to have superfluidity in the embedded hydrogen. Kudos to them.
Superfluidity happens because in this particular case, it didn't occur at first, but then it occurred when the clusters grew to 10 molecules. Why is it that it happens in that manner? Why do you have to reach some sort of larger number to be able to see this feature? And then is this something that we would be expecting to happen in just anything or only in, certain?
Occurs often in Bose-Einstein condensates. So typically in a regular flowing material, you would talk about it in terms of, here's this molecule, and this molecule is moving from here to here. Well, in it, the process of moving from here to here, it's bumping into this, and it's bumping into that, and it's bumping into that. And all these little bumping into things, that's the viscosity that's going on there, right? The viscosity is how it's bumping into things and how it's maybe lightly bound. So for instance, there may be van der Waals forces or something that are holding things, they're like minor little forces between molecules. So intermolecular forces that slow down the movement, right?
Okay, that's viscosity in a normal fluid. So now what happens in a Bose-Einstein condensate? Actually, Ian, tell us, what is a Bose-Einstein condensate, first of all?
What's a Bose-Einstein condensate? So there are two Oh, and we're going to talk about this later too. There are two fundamental types of particles out there. There's bosons and fermions. All particles, as we will hear, fall into one of those two categories. They're either fundamental particles anyway. They're all either bosons or fermions. And if you want to know the difference, stay tuned for one of our future picks and we'll talk about it. But bosons do have this property where they can all sort of inhabit the same energy level. So some atoms are bosons, and so they'll behave as bosons. Even though they're not fundamental particles, they'll behave as bosons. And so you can sort of get them all into this same energy level, which means you could squeeze them all into a ground state energy level, in their lowest possible energy level. Well, if you put all these molecules in the ground state, they're essentially all behave as one thing. It's almost weird to even describe the flow of something like that. And yet, as a bulk, it can seem to move from one place to another. So it's almost like you wouldn't have any of these interactions and things because everything's just all in the same state.
Something weird happens and they all kind of become like the same thing.
That's in the book. Of course, you can have them in fermions too. Fermions can have superfluidity as well. It just means that you don't really have collisions between the molecules anymore. And they just they stop interacting with one another and you just have this pure movement. It's a quantum mechanical phenomenon. The change to superfluidity is a phase change. So it's literally like a phase change going from a solid to a liquid or a gas to a liquid.
Right. And so I can ask, why did this happen when we reached 10 molecules? But then I could ask, why did water boil when we reached 100 degrees? It just changes phase. Okay.
Water's a weird one. I mean, why does water expand as it cools between 0 and 4 degrees Celsius? We don't know, but it's why we're here.
Let's not get into that. Let's not go in that direction. We've had too many diversions already. But,
yes,
every time we have one of these that come up, I say, well, what's the point of this? What's the practical use of this? This one feels like there may be some practical purpose towards it. And that's maybe why they spent 20 years going after it. What is it?
Well, so I want to push back a little bit on this. We are the Foundational Questions Institute. We are asking foundational questions. What's the importance of this? Sometimes it's knowledge for its own sake. I just want to say that. That's why we're here. This is why we care. Now, if you really want a really practical answer to this, supposedly this might have some potential applications in green technology because hydrogen is used in a lot of green technology. But again, I want to push back on that and just say, not everything has to have a commercial, practical, everyday application. It may down the line, but we're human beings. We ask questions about the universe.
Now, you see, I think you're pushing back because you know what you've got at number 3. And at number 3, I did have to smile. I had a little giggle at number 3 because I'm not going to say much about them. You're obviously going to introduce third place.
Third place, yes.
These feel very much like things that they just tickle you.
Yes.
They're just cute. They're kind of sweet, maybe a little silly. I don't know.
Well,
but yeah, you can introduce them. But as I was reading them, I was thinking, these are kind of lovely. Why are they the third most incredible thing that happened in the year?
Yeah.
And now you can push back as much as you want on my question of what is the practical significance of this?
Why are they so high on the list? Well, personal bias, I suppose. I will begin by relating a story from my undergraduate days that was related to me by a guy I worked with who told me about a company in Connecticut called the Electric Boat Company, and they made submarines. And he said they had this interview question. Now, I have to set this interview question up by explaining in the United States, in the middle of roads, you'll see round metal plates that if you pick them up, there's a hole down there. We hide lots of things underneath our streets, fiber optic cables and sewage lines and other sorts of things. We run wires and we run plumbing and stuff underneath our roads. So these things are called manholes, and it's a manhole cover. And in the United States, they're always round. And they are frequently round in the rest of the world. I think it was in Bratislava where they have a bunch of manholes that have funny art on them, like they're little people with eyes and stuff poking up above them.
I'm thinking about manhole covers that I've seen that are not round.
There are square ones. In fact, I know this because when I did my PhD, I got my PhD at St. Andrews in Scotland, and I got it the same year that Prince William and Princess Kate graduated. And for security reasons, they taped all the manhole, or not taped, they'd sealed all the manhole covers in town because they didn't want, bad actors getting down in there. And I happened to notice that. I noticed, they're all square. So all the manhole covers in St. Andrews are square. But at least most of them in the United States are round. So the question that supposedly, according to rumor, that Electric Boat Company used to ask as an interview question for potential engineers was, why are manhole covers round? So if you want to pause the podcast for a second and think about that, you can now do that. Go ahead, pause. Okay, welcome back. Now I'm going to explain why Electric Boat Company says they're round. And actually, this really is true. And if you stop and think about it, it does make sense. So all manhole covers, no matter what they are, in order for them to not fall down, there's a little lip inside, right? There's a tiny little lip. So you can set the manhole cover down and it just rests on a lip, but you don't need a very big lip for it to be secure. In fact, it turns out that if it's round, you need almost no lip at all, because a round shape is the only shape that, when turned on its side or something like that, will not fall through. That's why manhole covers are round, because God knows you wouldn't want one falling through and bonking some poor worker on the head. If you had a square one, for instance, assuming it had a reasonably sized lip on the inside, you could lift it up and turn it sort of diagonally and drop it through the hole. Unless you just made a really ridiculously large lip on that thing, which would just be like a waste of metal, right? So in fact, you could do this at home. Cut a square out of a piece of paper and then try to drop that square without bending it through the hole that you cut out when you cut the paper out. It very easily drops through. So the only shape that doesn't naturally fall through is a circle. So if you take this idea and you expand it to 3 dimensions, okay, so we're just talking 2 dimensions. Manhole covers are just 2-dimensional. So you expand it to 3 dimensions. Are there any shapes that cannot pass through themselves? And that is the question that one group of researchers actually set out to answer. And they found a 3-dimensional shape that cannot pass through itself. And it has been termed the noperthedron.
This is Jacob Steininger and Sergei Yurkovich who made this discovery. Ian, explain the name noperthedron to us, please.
So, this is a really fun story.
This is very silly. This is what I've written in my notes. This is very silly.
This is very silly. So, way back in the late 1600s, some person who no one knows who it was, but just someone, placed a bet with Prince Rupert of the Rhine. So Prince Rupert was a nephew of Charles I of England. Wasn't Charles I beheaded by Cromwell?
Yeah.
Yeah, I think so. I have this vague recollection that I have some ancestors who were part of the beheading. But anyway, Prince Rupert of the Rhine was Charles's nephew, and someone supposedly made this bet with him. This goes back to dice. So if you had 2 equally sized dice, is it possible to bore a tunnel through one die that's big enough for the other to slide through? Someone placed this bet that this couldn't be done. And supposedly Rupert won the bet, because it turns out you can, just like you can take a square, well, you can do this with a cube, which is all a die is. So the question is, are there any other shapes that cannot actually go through themselves? And these guys discovered one. And this is the noperthedron. So the reason it's called the noperthedron is because they refer to this property as the Rupert property in honor of Prince Rupert. And will it pass through? And if the answer is nope, then it's a nopert, as in Rupert, noperthedron.
I'm shaking my head silently. Yeah, a noperthedron.
Yeah, so nopert combines Rupert with nope. And so they found a noperthedron now, these guys. It was 1968, tetrahedrons and octahedrons were known to have the Rupert property, which is now what it's called. And the Rupert tunnels were found through dodecahedrons, icosahedrons, and even a soccer ball. Sorry, in the rest of the world, it's called a football. But yeah, they found one. It's a shape with 90 vertices and 152 faces. Yeah, it's kind of hard to visualize. I'm sure there will be a link in the show notes to it.
How do they find this out, by the way? I mean, they're not creating these things and drilling holes through them.
Oh, yeah, no. So it's a mathematical proof. That mathematical proof is very, very hard to do. And in fact, this is very interesting. These days, some of these, not all, but many of these new mathematical proofs are so complicated that they require a computational component. So the computer has to do a lot of the calculations for you because either there's no analytic solution or it's an analytic solution that would take someone, 100 years of living in Siberia with nothing else to do to solve. I'm not disparaging Siberia, by the way. It's probably very beautiful. So they used a lot of computational power. They would write algorithms to find, they call these, Rupert passages, the little hole that you would do. And actually, there was this one guy at Johns Hopkins who had his desktop working on something called a rhombocosidodecahedron, which is a solid made of 62 triangles, squares, and pentagons. He just had a little algorithm on his computer that would run it to see if that one had the Rupert property, which I think it does. And it was working on his laptop for 2 weeks. So there you go.
I was going to say, I can't believe that this was the one item on the list where I was going to be like, well, I don't even have to ask you what the practical implications are because there are none. It's just fun. And you started off with a discussion of manhole covers.
I love it.
And accessing sewer systems.
I love it.
And, security for the royal family.
Yes.
Not to mention your own dubious ancestry when it comes to royals and Oliver Cromwell.
Yes.
So
the first thing that came to my mind when I saw this report was, it's like that question from the Electric Boat Company from 30 years ago, which I don't even know if the Electric Boat Company ever actually asked that question. Like this three-dimensional argument would be that the sphere would be the only one that would work. But the claim is that this noperthedron is another shape that is not a perfect sphere, but that cannot fall through itself. So cool stuff.
So I'm just looking at the chaps who found the noperthedron, and they are not academic mathematicians anymore. I mean, they are trained in mathematics, and they've gone on to other things. I don't know what they've gone on to, but they are not academics. And I thought that's kind of interesting in the context of one of the items that we discussed in the bonus material about a mathematician who had not gone through conventional schooling.
Yeah.
No particular comment on that. I just think it's interesting.
And actually, we had, in a previous year, we had something, if I recall, there was some conjecture that was partially proven by a guy who was just an enthusiast in the UK who contacted some mathematicians, and they worked together. But he was, he had no training in math.
Yeah. Well, maths, it's not that hard. Maybe that's the takeaway from this. Surely anyone can do it.
Yeah. Sure.
Oh no, we've lost a bunch of our audience now.
I know. We're gonna lose more now because this actually is a tie for third place.
Ooh.
So it's not just these guys who found the noperthedron. They share this with a proof of another really cool and simple thing called the Kakea conjecture. I guess it was in 1917, which is almost 100 years ago, that Soichi Kakea posed this problem. If you imagine you have a pencil, in your hand, an infinitely small pencil, and you wanted to twirl it around. So maybe you're a fidgeter and you like to fidget with your pencil. You want to twirl it around in space, but you want it to cover every single point in space. How small an volume could it possibly trace out? You put this in 2 dimensions. You say area. So if I have a pencil on a table, and I spin it in place, it's going to spin out an area that's the area of a circle, right? But is that the smallest area that you can sweep out with a pencil? And it turns out the answer is no. You can actually sweep out a smaller area with a pencil. And there's a cool animation that I'm sure you link to in the show notes of this.
Okay, so we have a pencil and the goal is to spin it 360 degrees so that its tip covers every possible direction once? Or is that correct? I'm a bit confused.
It's really hard to do this with the podcast. If you just think about it for a second, it seems so obvious. So I got a pencil. Actually, I'm holding one in my hand right now. It's actually a pen, but I put it on the table in front of me. I could slide it up and down, and I could make a box. I could sweep out a box, all right? Or I could take it and I could spin it in a circle, okay? The circle that I would spin it in would have an area of pi r squared, or pi d squared over 4, so d is the length of my pen. Okay. The question is can I sweep out a smaller area such that the tip of my pen touches every sort of boundary point, right? And the answer is yes, you can, which seems counterintuitive. How would you be able to do that? Well, it turns out that if you slide it slightly as you're rotating it, you can make this little triangular shape. It was kind of like a weird triangular shape, okay? That is actually smaller than the circle of an area that you swept out with it by spinning it, but the tip of your pen has still touched every part of the boundary, right?
Thank you, because now that you've said that, although it sounds like it's really hard to visualize, I think I can visualize that. And I feel like there is some children's game or something when you're a kid, you know, when you're doing these kind of stencils and things. It's giving you that sort of sense of,
oh, yes.
You know, when you play with those things. And
I know exactly what you're talking about. The Etch-a-Sketch, not the Etch-a-Sketch. No, it's not the Etch-a-Sketch. The one where you had the little circles, there were gears, and you'd put a pencil in the middle and we'd draw out weird little shapes, and one of the shapes happens to correspond to the shape that you create in the 2D Kakea conjecture.
Yes.
I remember that.
Yes. So yeah, no,
yes.
So that kind of makes it may only make sense to me and you.
Yeah.
But your explanation does make sense to me, at least. And for everybody else, you can visit the podcast page, keyspace.fqxi.org/podcasts.
Yeah, so the question is what's the smallest volume that you can actually sweep through? And this is the three-dimensional Kakea conjecture is what they call it. The question is what is the answer? And these guys found it.
And this is Hong Wang of New York University's Courant Institute and Joshua Zhao of the University of British Columbia in Canada. And as with the Nopethedron, we'll be linking to another nice story with visuals from Quanta on the podcast page, qspace.fqxi.org/podcasts.
I'm not sure I could say that I could describe the exact shape. The three-dimensional one, if you look at the picture, Google Kakea conjecture, the three-dimensional one looks a little bit like the two-dimensional one. The three-dimensional one looks like a ball with spikes on it. And if you look at the two-dimensional one, it's kind of got a spiky look to it. I will say the four-dimensional Kakea conjecture remains open. The two-dimensional one has been solved. The three-dimensional one is the one that was just solved. The two-dimensional was solved a while ago.
And in an interview, mathematician Nets Katz said, "This thing doesn't need hyping up. It's a once-in-a-century kind of result." Which, I'm going to say, Ian, you're going to have to do some hyping up for me, because I don't understand. Why is this a once-in-a-century kind of result?
Maybe I'll quote Terry Tao, who's a very famous mathematician. He says, it's like perfecting a perpetual motion machine. They're getting more at the output than the input. Okay, so that's the three-dimensional one was what they just figured out.
Now, I mean, people are excited about this, not just because it's just weird and counterintuitive and cool, but because apparently other problems sort of rest on this proof being done. Do you know what those other problems are? You're looking at me like you don't know what those other problems are.
I have no idea what they are. Yeah, no, I have no idea what they're planning on going from this to what. I just saw it and I was like, wow, this looks cool.
There we go. Who cares what those other problems are? But some proofs that mathematicians want to chase after, and they needed this one.
I don't know.
You're going to kick yourself when you find out what is resting on the resolution of this conjecture.
Oh?
Because apparently the conjecture's resolution is a seismic shift for the field of, Harmonic analysis,
Oh, no. I didn't know that.
which studies details of the Fourier transform.
No kidding.
And so if you want to know more about that, go and listen to the bonus material because we spent a bit of time discussing that earlier. So
That's funny. Again, I'm such a foundational guy that I was thinking about the shapes looked cool. That's all I cared about.
well, now you know how useful it is.
Okay.
Has it lowered it in your estimation compared to the nopethedron?
I think they're still tied for number 3.
Okay. I'm still confused as to why these are number 3, but no, actually, I don't know. They're very pleasing.
Oh, meaning why they're 3 and why they're not lower. Why are they not runners-up? Well,
Yeah.
maybe I think partly because, I always like to throw a math thing in here. And I also think, so why are these higher than, say, the asteroid or the superfluidity? Because I think these say something fundamental about geometry, which is at the heart of everything. So I have to tell you a really funny story. This story goes back to my grandmother.
Right.
So my grandmother, Jean Hathaway Fisher Durham, was born in 1906. She went to college, this small liberal arts college in central New York state called FQxI College, and met my grandfather. It was a women's college, so he wasn't there. I can't remember how he met my grandfather. Oh, actually, I do remember how she met my grandfather. He was her high school teacher. But anyway,
Okay.
aside from that, she took a math class in college. It was plain geometry, and I have her math book from college, her plain geometry book. Let me just say that my grandmother absolutely hated geometry. Absolutely hated geometry. And if you page through this, she's doodled throughout her book. This was in 1925. So she was 19 years old, 1925. And you will see doodles and all the little shapes. She draws eyeballs on them and funny things. But she wrote this funny poem. And now I'm just trying to find it. Where is the damn poem? Yes, here it is. On page 281, under Proposition 10, theorem, which is the area of a regular polygon is equal to half the product of its perimeter and apothegm, she writes, my dear grandmother, if at the pearly gates St. Peter should say to me, all those who enter here must have their geometry, I should not stay and argue, for such is not my line. I'd say, goodbye, St. Peter, 'tis the other place for mine.
Wow. Oh, that's beautiful. That's brilliant. I love that.
So, geometry, it's the basis of everything, even though my grandmother hated it.
Well, okay, I think you've justified third place there for that. And also, I have to say, I've kind of warmed to these stories in the sense that after kind of a very somber start to this discussion and to our runners-up discussion as well, I think it's just nice to just celebrate things that are just lovely.
Yeah, absolutely.
That just make you go, oh.
Cool stuff.
That's fun.
Okay.
Yeah.
So, now, number 2. And I have to start off with number 2 by giving a disclaimer. Guess I'd call this a partial conflict of interest. I'm not on this paper, but one of the authors I'm going to mention is a co-author and collaborator of mine. But that's not why I awarded this number 2. It's just a very deeply foundational thing. So there were some conflicting reports that came out in early 2025 about something called paraparticles. So what are paraparticles? So there are 2 fundamental types of particles, fermions and bosons. Fermions are particles that have half-integer spin. So they have spin half, spin 3 halves, whatever. Most normal matter is made up of fermions. So electrons, quarks, and then as a result, protons and neutrons are half-integer spin, etc. And then bosons. Bosons are like a photon. A photon is a boson. And they have integer spin or zero spin. A photon has a spin 1. And each of these different types of particles, fermions and bosons, obey a different set of what are called statistics. If you look at their statistical distribution of states, in a given situation. They have a different statistical distribution. So bosons obey what's called Bose-Einstein statistics. Fermions obey what are called Fermi-Dirac statistics. Photons are kind of this special case. Photons are a black body, which is a separate distribution. But the whole idea is that there's this thing called the spin statistics theorem, and there are only these two types of particles, fermions and bosons. The question is could you have a particle that's, say, a superposition of fermion and a boson, or some weird thing in between a fermion and a boson? Now, two interesting papers came out addressing this right around the same time. They're not in direct conflict with one another. One says that yes, paraparticles can exist.
So this is a paper by Zhiyuan Wang, now at the Max Planck Institute of Quantum Optics in Germany, and his former advisor Caden Hazard of Rice University in Houston, Texas.
However, that paper really only applies to exotic materials. So you could see something like paraparticles in exotic materials. There would be something a little bit like if people know what phonons are, which are particles in materials. They're sort of quasi-particles. They're not real particles. They're quasi-particles in materials. Paraparticles would be something like that. So that paper claims that paraparticles can exist. Now, another paper came out around the same time, co-authored by Marcus Mueller, who is an FQxI member and a collaborator of mine. Marcus and his group, one's a PhD student, maybe one's a postdoc. But anyway, they came out with this paper that says that, in fact, at the fundamental level, so at the deep foundational level, elementary level, there can be nothing but bosons and fermions, that you cannot have any paraparticles. So at the elementary level, we will never see an elementary paraparticle exist. So technically, the two papers do not contradict one another. But at the foundational level, the one that says the most foundational thing is the paper by Marcus that says you can't have a superposition of a boson and a fermion at the most fundamental level. It just won't exist.
So I will say, I think you can get away with the conflict of interest here with Marcus Mueller, as long as you don't tip him off that he's on the list so that he can get his free hoodie. He'll just have to stumble upon that realization himself, because otherwise that's just too corrupt, I think, if you're sort of giving your friends free hoodies.
Well, so I will say this. I did not tip him off that he was on the list. I did tip him off that he was under consideration for the list because I had questions.
Oh, I see.
I wanted to ask him about the paper. So I was emailing him. So I don't know whether he gets a hoodie or not.
Yes, it's just tricky.
We'll see. I didn't tell him whether he was made the list. I just said, you could think of it like this. They, when the Nobel Prizes go out, they call up potential winners and interview them. And I suppose if if it doesn't work out, they don't give you the Nobel Prize. So, just because you were interviewed by the Nobel Committee doesn't mean you're going to get a prize.
Who knows? He's probably hitting refresh on the FQxI website every day, every hour, just to find out now if he's made the list now. Okay, so let me ask you some questions, because there's a lot going on here.
Yep.
I mean, we're talking about the phrasing of this is a third kingdom of particles. So this whole paraparticle thing, it's quite a big deal if it's true, if these are allowed.
Let me actually just, first of all, I want to challenge, there was some hype around this by well-meaning authors, and I want to make sure it's understood that, again, going back to the real answer is that at the fundamental level, there isn't a third kingdom of particles. So there are just fermions and bosons. The existence of these paraparticles, they would be in, again, exotic matter, which would not necessarily be unexpected, because all sorts of strange things can happen when you start to put systems together, and you can get, it's an emergent property. I hesitate to say there's a third class of particles, because there really isn't. The whole point of Marcus's paper is that there isn't. They're not fundamental thing. I think that's the most important thing to take away from this, because I am worried about everybody thinking, oh, there's this new category of particle. But in fact, again, it's an emergent kind of thing, right?
Just to sort of drive home that point about what a quasi-particle is. The thing about a quasi-particle is it sort of exists within the confines of the material, and it's the result of sort of the collective phenomenon of actual particles
Correct.
behaving together in some kind of way that makes it look like they are little particles inside the material.
Yeah.
But you can't like pick one up and take it out and have it
Nope.
exist outside of that material.
Nope.
So you're basically saying in exotic matter you could see this kind of weird paraparticle thingy.
These quasi-particles are basically just like excitations in energy levels that are clumped together in such a way that they look like particles, but they're not. You know, they're just some collective behavior of a bunch of excitations that all happen to exist near each other in a particular material.
You sort of mentioned they're kind of somewhere in the middle of being a fermion and a boson. What kind of properties would they have in that case? Or could they have? Might they have?
There are quantum computing applications that people would be interested in looking at these paraparticles in relation to. So someone talked about a Rydberg quantum simulator, or Rydberg, I've heard it pronounced both ways. So that didn't really answer your question.
Just to say, in that exotic state of matter, these quasi-particles could do things like bosons. They can pack an endless number of particles into the same state,
Which we talked about earlier in the bonus material.
Yep, and fermions can't. But paraparticles could be somewhere in the middle in the sense that they could pack a few particles into the same state, but not sort of an infinite number.
Right.
That's what you mean by being halfway through.
But again, the reason this is number 2 is actually not for that discovery. The reason for this is really Marcus's result that at the fundamental level, there never will be paraparticles.
Okay, so that's interesting. It's the negative result that's more interesting to you.
It's the negative result, yes.
Let's talk about Marcus Müller's paper then, and you've discussed it with him. How do you go about proving then the negative of, no, you couldn't ever have anything other than these two?
Yeah, that's interesting. So Marcus approached this from the standpoint of quantum reference frames. There's a fundamental thing that we teach in introductory quantum mechanics called exchange symmetry, which means if I have two particles and I swap them, I swap places, what happens? To put it another way, imagine I have two dice and they're the same color and they look exactly the same. And I have them sitting on a table and, one's a 5 and the other's a 3. And you walk out of the room and you come back in the room. You'd have absolutely no way of knowing if they were exactly identical dice if I swapped them. You couldn't tell. Particles don't behave quite as straightforward as that, but they have a certain symmetry under exchange when you swap them. So maybe I should step back a second and say what swapping actually does in fermions and bosons. So if I swap a pair of bosons, the wave function for the pair of bosons is symmetric. It's like I can't tell the difference. For fermions, it's what's said to be anti-symmetric. So if I swap two fermions, the symmetry is anti-symmetric, which means I pick up a negative sign. What that exchange looks like is somewhat dependent on the reference frame that you're looking at it from. In quantum mechanics, if we have a system of two particles, then we can actually write a single wave function for the whole system that includes both those particles. Now, this is an important point for our listeners who may not know this. So when we talk about a wave function for something, I can write a wave function for a particle in lots of different ways. There's not like a single wave function for a particle because there's this thing called the Born rule. And according to the Born rule, the square of the wave function, so the wave function is this mathematical function, and when you square it, you get a probability. So if I write my wave function in terms of, let's say the variable is space, then squaring it at a given point in space gives me the probability that I will find the particle at that point in space. Likewise, I could write a different wave function for the same particle that is in terms of its momentum. And then if I square this wave function, then the square of the wave function for a given momentum gives me the probability that I will find that particle to have that particular momentum. Okay, so let's go back to the spatial wave function. Like I said, I can write a wave function for the whole system of, which is in this case is two particles, I can decompose that wave function in several different ways. One way I can decompose that wave function, because it's a spatial wave function, right? So it's describing and how the system exists in space. So I decompose it so that I have the components of the wave function that describe the particles being far away from each other and the components of the particles being close to one another. If I decompose it that way, so I take the two components for when the particles are close to one another and I swap them. I'm swapping one particle for the other, but only in the part of the wave function where they're close to one another spatially. Okay, so the far away stuff isn't happening. And doing that, depending on whether it's a fermion or a boson, this is sort of the way that Marcus and his group showed that you can't actually have a mixture of a boson and a fermion. So there are a couple of questions about this, but it's not exactly clear what you would have. So let's say you had two paraparticles, two fundamental paraparticles. What would it be? Would it be symmetric or would it be antisymmetric? Would it be some mixture of a boson and a fermion when you do this? And the answer is you can't.
So, result.
No paraparticles.
No third kingdom.
No third kingdom.
So I'm not sure if that's a happy ending or a sad ending on that one.
I think it's a happy ending.
It's a happy ending.
Yeah, everybody wants, wouldn't it be cool if we had these fundamental paraparticles? Well, yeah, sure, maybe. But, it's also interesting to know that they can't exist. That's a pretty profound and deep, deep thing, that they can't exist. It's not possible.
So if they could have existed, would this be number one, or would this have been lower down?
Oh no, if they could have existed, this would probably be number one.
Right, okay.
That would be really wild. Because you'd have to rewrite the standard model of particle physics if there were fundamental paraparticles. I don't want to play down the results of these guys who showed that paraparticles can exist in exotic states of matter. I think that's a cool and important result. It means we could observe some neat things in some exotic materials. That's cool. But fundamentally, at the deepest level, what's the universe made of? Well, it turns out that it really is just fermions and bosons.
So we can take comfort in that.
Yeah, that's a deep result.
Okay, so that was number 2. It could have been number 1 if it had gone in the other direction, but it didn't.
Yeah, it didn't.
And so it has been pipped to the post. It has been beaten out by something. But what?
Ba-dum, roll drums. So, this year, I have to say, I taught cosmology this semester. I literally just finished teaching cosmology. I had to actually add this to my class. So this was cool. Let me back up a second. So the James Webb Space Telescope has opened up new horizons to us. And one of the curious things that it picked up, because it has such good resolution, is it was looking at views of the very early universe, and it picked up these things called little red dots. The question was, what were these little red dots? They weren't pixel problems. They were legitimate things. And in fact, they were even able to figure out that these things were spinning. So they're actual things. What were these little red dots? Well, one of them, which is labeled QSO1 by some, although it's actually got a different label. It's Able something or other. I don't remember. It's got some long technical number to it. But QSO1, QSO stands for quasi-stellar object, or quasar. So I guess I'll give the punchline first. So they discovered that this quasar is a supermassive black hole, but that doesn't have much material around it. And the material that is there is almost entirely hydrogen. I should also say this is one of the most distant objects that's been observed. So it's not only very distant, it's also, we're looking very far back in time.
This was the work of an international team led by Ignace Ujbales, I'm sorry about the pronunciation there, at the University of Cambridge in the UK.
Now, let's unpack what that means. I guess the way to talk about this is to go back to the formation of the universe and how we think things have gone. So there's, of course, the Big Bang, which is a hot Big Bang model. So big explosion, lots of heat. That leftover heat is the cosmic microwave background radiation. Then, after the big explosion happens, stuff starts to cool and you start to get matter. First, you get some leptons and some gluons, and then the gluons form protons and neutrons, and eventually things cool out. You end up with protons and neutrons that form atoms and electrons, et cetera, et cetera, et cetera. Somewhere in there, and it's not exactly clear where, we also get dark matter. The dark matter forms somewhere in there. Now, there are two scenarios for how dark matter can form. We don't know what dark matter is, and this is not the same thing as dark energy if you listen to the runners-up. Dark matter is some kind of matter that's non-baryonic, so it's not your typical protons and neutrons and stuff. And most galaxies have a halo of dark matter around them. And we know this because of observing how they rotate and how they gravitationally interact. They seem to have more mass than they should. And so we've been studying dark matter and modeling it for a long time. We still have never seen any dark matter. Lots of theories on what it possibly could be. The two models that emerge, one's called the hot dark matter model and one's called the cold dark matter model. And generally speaking, we accept the cold dark matter model as being the one that most closely matches our own universe. In the cold dark matter model, after all this cooling, you have the protons and the electrons and neutrons, and then you get some atoms and things. Throughout all of this, you get random fluctuations thanks to quantum mechanics and things. So you get random fluctuations in density, areas where you'll have a little bit more stuff and areas where you'll have a little bit less stuff. In theory, this also happens with the dark matter itself. So the dark matter tends to clump, and then you get some primordial hydrogen and helium is formed, and maybe you get little traces of lithium and beryllium. They start to fall into the gravitational wells of the dark matter. And so they clump partly because the dark matter has clumped and starts to coalesce to form stars. And then the stars collect to form galaxies. And then the galaxies collect to form clusters. And then sometimes the clusters form superclusters. So it's a bottom-up scenario of how stuff forms. You form stars first, and then you get galaxies, and then you get the other stuff. In a hot dark matter model, it's a top-down model. You actually get the galaxies first, these giant structures first of just gas, and it's the gas that coalesces first into galaxies and then into stars and planets and things like that. We're fairly certain, for many reasons, that we do not live in a hot dark matter universe. We live in a cold dark matter universe. So here's the thing. Pretty much all galaxies that we know of have a supermassive black hole at the center. And there are a number of different ways that you can form a supermassive black hole. Again, we're talking about a supermassive black hole. So we're not talking about black holes that are formed from the collapse of stars. We're talking about black holes that are formed from when you just get so much stuff in one place. In any case, the supermassive black hole is usually not the first thing that's formed. In the cold dark matter model, you form the stars, and then a galaxy, and then you get enough stuff in the center of that galaxy, and gravity starts to pull everything together, and you create a supermassive black hole. But you have to, in the cold dark matter model, you have to have the galaxy form first, and then the supermassive black hole comes, which means that all supermassive black holes have a galaxy around them, which means you've got lots and lots and lots of stuff. You have stars, and you've got lots and lots of other material. So not just hydrogen and helium, but you've got all sorts of elements. Not a lot of them, but you have all sorts of other elements. Well, Quasar 1, QSO1, doesn't have that. It's a supermassive black hole that seems to only have hydrogen and maybe little traces of helium, and very little at that, which means it's a nearly naked black hole. And the question is that where did it come from?
Mm-hmm.
What is it? How did it form? How did we get a supermassive black hole that's nearly naked in the early universe under a cold dark matter model? Where's all the stuff it should have formed from?
So you know who would love your choice of number one?
Who?
Bernard Carr,
Ah!
who we interviewed quite recently for the Halloween edition of the podcast and more, who spoke about, well, among other things, poltergeist and primordial black holes. And I will put a link on the podcast page, qspace.fqxi.org/podcasts, where he takes us through, this was recorded earlier this year, what we do know about black holes, the ones that are born from the collapse of stars, that we understand fairly well, the stellar mass black holes, and the fact that we know that there are supermassive black holes, but we don't really exactly know where they come from. And then his own favorite things that he worked on with Stephen Hawking when he was a student and has continued to work on for 50 years, primordial black holes.
Here's the thing, though.
Yes.
From my understanding, the primordial black hole models, most of them predict much smaller primordial black holes.
We should explain what a primordial black hole is, because I kind of jumped into that, but we never actually said what it is. So what is a primordial black hole? For the people that haven't listened to Bernard Carr's podcast interview, but they really should go and listen to that podcast interview.
So basically, a primordial black hole is almost exactly what it sounds like. And it's this idea that in a very early universe, there might be these extremely dense pockets of matter that form at some point. You have these fluctuations in density throughout the universe. Some areas are overdense, some are underdense. These would be overdense, like to the nth power. Like they're really, really overdense. So much so that they collapse into a primordial black hole, and it would be very small. Because actually, primordial black holes is one of the ideas that people had for dark matter, was that, maybe it's just primordial black holes. But in that case, we'd see gravitational lensing and things that, small scale that we don't see. But anyway, they're typically smaller. Like a primordial black hole is assumed to be a smaller thing, as opposed to this is massive. It's a supermassive black hole specifically. I am not familiar with any primordial supermassive black hole theories. I'm sure there's probably a few out there because there's all sorts of things out there. But it's not something that is typically discussed in the cosmology community that I'm aware of. So I don't know if Bernard has another idea. But anyway, that's my answer to the thing about them being primordial black holes. I don't think this is a primordial black hole.
Oh, but then what is it? What is it? What is it? We will put some links to some articles with some ideas on the podcast page. But yeah, what kind of ideas are there out there? People have put forward ideas and they don't seem to be really convincing everyone at this point.
Well, I don't think anybody's got a good theory about what this is.
Yeah.
The primordial black hole is one. There's one called a not quite primordial black hole, which is, again, an overdense spot that collapsed sometime after the Big Bang, but before other things started forming. Or it could have actually formed very quickly in a galaxy under the typical way and then eaten up the rest of the galaxy. So the idea is that if you run the galaxy sequence long enough, they should eventually eat up the whole galaxy, presumably. One would assume that everything orbiting the supermassive black hole will eventually fall into it. In that sense, we should eventually see, these supermassive black holes that don't have a whole lot of stuff around them. However, the amount of time it takes for that to happen is really long. And this thing is not that long after the Big Bang. Again, this is based on the cold dark matter model. So it's possible that maybe the cold dark matter model isn't quite right. Now, the hot dark matter model doesn't match either. So maybe there's some third option that will explain this and will also explain the way the dark matter is distributed and how things form now. We don't know. But like I said, nobody has a good explanation of this yet.
But I mean, that's always the problem with cosmology, is that you can come up with a model that will help you. I mean, you can change things and you can tweak things and you can explain the one weird anomaly that you're trying to explain, but then everything else that you could previously explain goes out of whack. And then
You're right, exactly.
So that's going to be the issue. If they start messing around with the cold dark matter model and adding different elements, it's not going to be able to fit with the cosmic microwave background. It's not going to explain, like you say, the distribution of dark matter around, and it's going to cause all sorts of other headaches. So I'm trying to think of the last time number one on your list was a cosmology story.
Oh, I don't know. I know I've done them before.
Yeah, but it's been a while, I think. It's been a while. Maybe the Event Horizon Telescope? Was that number one?
Could
I can't
be.
remember.
Could be.
No, but the reason I'm saying that is because I feel like it takes a lot for cosmology to get onto. I mean, look, dark energy weakening didn't even make it onto your list. Like, I feel like you have a bias against cosmology, which, fair enough.
Oh God, I don't. I am a latent cosmologist.
Well,
so I have no beef against cosmology.
I'm not saying that to accuse you. I'm just saying that, this gives you a sense of how big this story is.
Yeah.
For a cosmology story to have made it to number 1 on your list.
Let's just put it this way. This was a big enough story that I changed the class I was teaching at that time to incorporate this because I'm using this textbook, the standard undergraduate textbook by Barbara Ryden, Introduction to Cosmology. And of course, it's not in there. As I'm getting to this stuff with the structure formation, I'm like, and this was towards the end of the semester. I said, all right, I have to add something that's not in the book because this is just discovered. Because I'm reading this stuff in the book and I'm like, well, how do we explain QSO1? That doesn't fit here. So I said, if it changes the way I'm teaching, then it's definitely going to be near the top of my list.
I mean, we've been saying for years that, this JWST will give us a whole new window on cosmology, on the universe. We say that about gravitational waves and all of these things.
Yeah.
It seems to be happening now after all that long wait of, this will happen one day.
I think as a quantum person, I did used to do cosmology, so I'm not super active in the cosmology community anymore. I teach it and I do keep up with some of it. But, it seemed like we really had our handle on the lambda CDM model, lambda being the dark energy. And yes, the dark energy is slowing, maybe. Like, that was one of our runners up, but it's still there, right? Nobody's denying that the dark energy is still there. And yes, we have to figure out why it's slowing. What does that mean? But it's still there. This just challenges the whole lambda CDM model. How did it form?
You seem very grouchy about that. Usually you end on this optimistic high note of, this is so profound. This is wonderful. And you're just like, ugh.
Well,
what have they found now?
Yeah, what have they found now? Oh, no. This thing just ruins all our theories. Yeah. I don't know.
It's the mice. They've put you in a bad mood, I think.
It's the mice I don't know. It's a grouchy year. I don't know.
There we go. Number 1, we can say that we are rewriting the cosmology textbooks.
We are. Yes.
We are. Literally, Ian was doing it during his course.
Cosmology, holy cow, this stuff changes so fast that textbooks that I have and I used when I was in school, not that they're invalid, but they're missing huge things that are just not there. And now we have to change them again.
So if you want to keep up to date with what is happening, then keep a watch out for Ian Durham's Masterclass, which will be coming. This time we really, really promise it will be coming.
Yes.
In the next year.
Yep.
So that's something to look forward to for the new year, for 2026.
I have to say, in response to that, so yesterday, here in America, we have a bit of an obsession with something called American football. And I was at a game for my favorite team, the Buffalo Bills, who were playing the New England Patriots. And I was walking out of the stadium, and some woman, I ran into another Bills fan there. She was from Colorado. And she was really into time travel stuff. And I told her about my masterclass.
Oh.
I said, memorize this because, it's late. I'm like, I didn't have anything to write it down. I said, FQxI.org. And she's like, FQxI.org. Okay. I'm like, masterclass on time is coming.
Time and consciousness and the cosmos. And if you just can't wait for Ian's masterclass, then please do head over to qspace.fqxi.org/podcasts and click the link for Complexity in the Cosmos by Julian Barber. It's our first FQxI masterclass. I'm really excited about it. We've put in a lot of work here. If you use the link on the podcast page, or if you go to the main Q Academy page and enter the coupon code podcast70, you will get 70% off. So you will only need to pay $3.30 instead of $11 for your first month subscription. Or if you prefer to make a one-time payment, then instead of having to pay $55 for 6 months of access, you will only need to pay $16.50. So, yep, massive bargain. Don't miss out. That 70% discount is only valid until the 7th of January 2026. So start the new year with a pledge to learn about shape dynamics, to redefine gravity the Julian Barber way in terms of complexity, and to rethink the Big Bang, causality, and time's arrow, and earn your FQxI certificate and give a little donation to FQxI along the way. We are a non-profit. The money that you give will come back towards making more masterclasses, more podcast episodes, and even funding more foundational physics research. And fans of this podcast will have heard about how Julian Barber's framework suggests that our Big Bang spawned two mirror universes, or Janus universes, with opposing arrows of time. So there is lots to learn in Julian Barber's alternative take. Join hundreds of other Happy Q Academy students now. It's a fun little course. It's not going to be as intense. He's not going to make you work as hard as Ian Durham will. But but yeah, you can have some fun with that. Links are on the podcast page and on qspace.fqxi.org. Look for Q Academy.
Julian is always entertaining.
He really is. He really is. He's lovely. So there we go.
There we go. Congratulations to the winners.
And there will be links to news articles and relevant papers for all the items that we discussed in the top 5 and the runners-up. And if you didn't listen to the bonus material where we discussed those runners-up, then you should head over to the podcast page, qspace.fqxi.org/podcasts, and do so now. You'll also see links to a lot of the visuals that we spoke about there too. And if you are one of this year's top 5, then send us an email at podcast@fqxi.org or contact us on socials at FQxI or at FQxI Physics. We're just about everywhere. You should follow us on socials anyway, because you'll see more material related to the countdown with Ian Durham too. I should also say, those waiting patiently to hear more from Bernard Carr and also Nihaya Shafshordi on the podcast, as I have been promising on previous episodes, don't worry, those follow-up interviews will be coming in 2026. Thank you very much, Ian.
Thank you, Zeeya.
For another wonderful list. Even if you were a bit grumpy at the end, I feel like the list has let you down this year.
I don't think I was grumpy.
I feel like secretly you wanted to put the two maths ones as number 1, but you just couldn't. You couldn't justify it. But that's where your heart is. I could tell.
No, actually, I promise you that when this one came out, I said, that's my number 1.
Okay.
If it makes me change my class in the middle of teaching it, it's number 1.
There you go. For all of our listeners, have a happy new year.
Happy New Year.